next problem that we're going to attack using the dynamic programming technique is the so-called chain matrix multiplication problem. The input in this problem consists of n matrices, which we denote here by A0, A1, and so on, an minus 1. And what we need to find is the minimum cost of multiplying these n matrices. We will now clarify what we mean by saying the cost. Okay, first of all, recall that in order to be able to multiply two matrices A and B, we need to ensure that the number of columns of the matrix A is equal to the number of rows of the matrix B. This basically means that the number of columns of the matrix AI should be the same as the number of rows of the matrix AI plus 1. Right? So this allows us to denote the sizes of our n matrices by m0 times m1, m1 times m2, and so on. So basically the size of the matrix AI is equal to mi times mi plus 1. Okay? Then recall that even for square matrices, matrix multiplication in general is not commutative. Namely, there are matrices A and B such that A times B is not equal to B times A. This means actually that even if our matrices were square, we would not be able to actually swap the order of matrices. The same holds for four matrices. So if we need to multiply A by B by C by D, then there are at least two possible orders. We may first want to multiply A by B, then C by D, then multiply two results, or we may first multiply B by C, then multiply A by the result, and finally multiply the result by D. Okay? So the cost of multiplying two matrices of dimensions P by Q and Q by R we define to be equal to PQR. This actually reflects the following fact. So the resultant matrix has dimensions P by R, right? So it has P by R cells. And to compute the content of each cell, we need to multiply a row of the first matrix of size Q by a column of the second matrix of size Q. So it definitely can be done in time big O of Q. So definitely we can compute the product in time big O of PQR. In fact, faster algorithms are known for computing the product of two matrices, but for the time being, let's just assume that the cost of multiplying two matrices P by Q and Q by R is just equal to PQR, even without any constants. And before designing an algorithm, let me illustrate you that even for small data sets, for example, for four matrices, the order of multiplication actually matters. So consider four matrices A, B, C, and D of the following dimensions. So 50 by 20, 20 by 1, 1 by 10, and 10 by 100. And in the first case, I assume that we are going to multiply their product as follows. So we first multiply B by C, then multiply it by D, and finally we multiply A by the result. So after the first multiplication, namely B by C, we get a matrix B by C of dimensions 2 by 10, and we pay for it 20 by 1 by 10. Right? Our next operation is multiplying this result by D. Then what we get is a matrix of dimensions 20 by 100, and we pay for it 20 by 10 by 100. Okay? Then finally we multiply A by the resulting matrix, and we pay for it 50 by 20 by 100. As a result, the total cost of this multiplication is roughly 100,000. Okay, now let me show you that in some other order of multiplication of the same two matrices, the cost is much lower. Okay, so assume that we first multiply A by B and then multiply it with C by D. Okay, so for the first multiplication A by B, we pay actually 50 by 20 by 1, and you see that we have this very thin matrix. Then we multiply C by D, and we pay for this 1 times 10 times 100, and again we see that here we get a matrix whose height is very low. And finally, we multiply these two resulting matrices and we pay 50 times 1 times 100. So the resulting cost in this case is just 7,000, which is much lower than in the previous one, in the previous case. Right? Now, an essential observation that will help us to design a sub-problem to define a sub-problem in this case and to finally design a dynamic programming solution is the following. Any order of multiplication of our matrices can be conveniently represented as a binary tree. Okay, where we have our matrices, our initial matrices at the leaves, and each internal node actually multiplies two matrices. So, for example, the first tree shown here on the slides corresponds to the order where we first multiply A by B, then multiply the result by C, and multiply the result by D. The second one corresponds to the order where we first multiply B by C, then multiply the result by D, and then finally we multiply A by the result, and so on. So in general, if we consider such a tree not for 4 matrices but for n matrices, and for example, let's consider its 4 subtrees. Okay, then what we see is that the left subtree here multiply matrices starting from 0 to, say, I minus 1. The next one will multiply matrices starting from AI minus 1 to from AI, to AJ minus 1. The next one will go from AJ to AK minus 1 for some K, and finally the last one, the rightmost one, will multiply matrices starting from K to N minus 1. Right? So the pattern that emerges here is that any subtree in such a binary tree multiplies matrices from I to J minus 1 for some parameters I and J. Okay? And this suggests that we define a subproblem as follows. So let M of Ij be the minimum cost of multiplying matrices from I to J minus 1. Okay? So we know that it can be represented as a tree, and in turn, if we consider this tree, then it has a root and 2 subtrees, right? And we know that in the subtrees, what is computed is the product from I to K minus 1 in the left subtree for some K, and in the right subtree from K to J minus 1. So what we basically need to do to compute the value of Mij is to go through all potential values of K. And this is what we do actually to define the recurrence relation. So finally, M of Ij is actually equal to the minimum overall K, which is greater than I and smaller than J of the following quantity. M of Ik plus this is the cost of multiplying matrices from I to K minus 1 plus M of Kj. This is the cost of multiplying matrices from K to J minus 1, and plus the cost of multiplying 2 results. And the results actually have dimensions Mi times Mk and Mk times Mj. So the cost of multiplying these 2 matrices is Mi times Mk times Mj. Okay? There is also a base case where J is equal to I plus 1. In this case, we have a single matrix, so there is nothing to multiply, so the cost in this case is equal to 0. Okay, so when we have a recurrence relation, as usual, it is just a technicality to convert it into a recursive algorithm, So in this, and you see this algorithm here on the slide. So again, we have a table T, which is just a dictionary. Again, what we do is what we need to compute is M of Ij. We pass these 2 parameters to our procedure, and we only start computing it if it is not in our table yet. So if J is equal to I plus 1, then we are in the base case. Then we say that then the result is equal to 0. Otherwise, we compute it using our recurrence relation by making recursive calls where K ranges from I plus 1 to J minus 1. So for each such recursive call, we check whether the resulting value improves our current solution. If it improves, we actually store it. Okay? So in order to convert this recursive algorithm into an iterative one, we need to actually make some little effort in this case, because in this case it is not immediately clear what is the right order of all subproblems. So, namely, what we need to do is to go from smaller size subproblems to larger size subproblems. Since in this case each subproblem is actually specified by two parameters I and j, it is natural to use a two-dimensional table to store all the results. At the same time, we cannot fill in this table, for example, row by row or column by column, because it will not give us a possibility to go from smaller size subproblems to larger size subproblems. And at this point, it is important to define what is the size of a subproblem. It is natural to say that the size of a subproblem is the number of matrices that needs to be multiplied, right? So the size of a subproblem is just j minus 1, which basically means that we need to start with the size equal to 1, then proceed to size equal to 2, then proceed to size equal to 3, and so on. So we fill in our matrix diagonal by diagonal, like this, right? And this gives us the following code. So in this case, we use a parameter s, which actually denotes the size. So s, when s is equal to 0, this is or equal to 1. This is just our base case. So we initialize all such cells with 0. Then we gradually increase s, starting from 2 to n. And for each such s, we consider all the subproblems whose size is s. And we do this just by iterating over all I, and j is computed as I plus s in this case. And then we compute the value using our previous recurrence relation. So this gives us an algorithm whose running time is cubic. It is n cubed. So this is basically just because we have 4 nested loops. Or put it otherwise, we have n squared subproblems, and for each subproblem we need a linear amount of work to compute the result. So finally, to unwind a solution, we basically need to go from the final cell, which is a cell with indices 0 and minus 1, and we need to go back to the initial diagonal. So we start with the cell 0n, and for each such cell we need to find a choice leading to this cell. Namely, we need to find a k between 0 and n, which led to the result of this particular cell. So by unwinding a solution in this manner, we will actually construct this tree, right, which represents the optimal order of multiplying our matrices. Finally, to arrive to the right notion of a subproblem from a different side, namely by optimizing a brute force solution, one can implement the brute force solution as follows. So the brute force in this case is to enumerate all possible binary trees, and actually to go over all possible binary trees and to find the best one. And actually, to optimize it, one just notice that when we find a subproblem, when we compute the value of a subproblem, we do not need to know the shape of this tree. We only need to know what are the matrices that are multiplied in this particular tree.